Hi, my name is Brian Conlon, and today I'm going to be presenting phenylketonuria, an autosomal recessive human disease. So in this first slide, I have a family pedigree, and first I'm going to direct you to the legend, which is in the top right corner of the slide. So the circles are going to be females, the squares are going to be males, and the lines are going to represent the relationships between the individuals or the statuses of the individuals. So for the females, a white circle is a female that's not affected by the disease. You're going to see that most of the pedigree is white because this is a recessive disease. So more people will not be affected by the disease than will be. A half white, half blue circle is going to be a female carrier of the disease, so that's a heterozygote. So it would be a female who carries the disease in her genotype, but she doesn't express it in her phenotype because this is a recessive disease. And a blue circle is a fully affected female, so a homozygous recessive female. Now, similarly for the males, a white square is a homozygous uh, the homozygous non-affected, so the homozygous dominant male. A white, half blue, half white square is a heterozygous male, so that's a male who carries the disease in his genotype, but he doesn't express it in his phenotype. And a fully blue male is a homozygous recessive male who's going to carry the disease fully in his genotype and express it in his phenotype. If you see now on the right of the legend, if you see a slash going through any of these individuals, that indicates that the individual is deceased. The vertical lines indicate the lines of descent. So the older individuals start at the top and they work their way down to the younger individuals. Horizontal lines are lines of marriage. So as you can see on the top, the two individuals at the very top are married or were married. And then if there are siblings, as you can see right below those the two top individuals, they are horizontal lines as well, but just to differentiate between siblings and marriages, the siblings go up first and then across. So you can differentiate them that way. Now, getting into the actual family pedigree, it starts with a male who was a homozygous recessive carrier and expressor of phenylketonuria, who married a female who was homozygous dominant, so she didn't carry or express the disease at all. They had two children, and they're annotated as I1 and I2. They had two children, generation 2 and generation 2-4, and the numbers come from the ages. So it's oldest to youngest in each generation. The Roman numerals denote each generation. So I2 and I4, the two daughters, were both heterozygous recessive carriers. So they didn't express the disease, but they carried the genotype. 2, the older daughter, married a man who was also a recessive carrier of the disease. And they had, so I'm on the left here, they had two sons. One son was a homozygous recessive expressor of the disease. That was 3-1, and the other son, 3-3, was a heterozygous heterozygous carrier of the disease. So if we stay on the left here, the 3-1, the homozygous recessive son, he married 3-2, a woman who was homozygous dominant, so she didn't have the disease at all. They had one daughter, 4-1, who was a heterozygous recessive carrier of the disease. She married 4-2, a man who was a homozygous dominant, had nothing to do with, had no disease at all, and they had one daughter, 5-1, and she was also a recessive carrier of the disease, and she married 5-2, a man who does not carry nor possess the disease at all. So going back to the right side of the slide, so if you remember, 2-4 was one of the heterozygous carrier daughters. She married 2-3, a man who didn't express the disease at all. They had one daughter, 3-4. She was a heterozygous carrier of the disease. She married 3-5, a homozygous dominant man who did not carry the disease at all. They had one daughter, 4-3. That daughter did not carry the disease at all. She was also homozygous dominant. She married a homozygous dominant man, 4-4. He did not carry the disease, so their son, 5-3, did not carry the disease either. In terms of phenylketonuria, in terms of its genetic background, like I said, it's an autosomal recessive disease. It causes a deficiency in the phenylalanine hydroxylase enzyme, which is an enzyme that catalyzes the hydroxylation of phenylalanine to tyrosine, which is rate limiting in phenylalanine catabolism. So essentially what happens is there's a buildup of phenylalanine in the body, which causes a lot of issues. The gene that codes for this enzyme is called phenylalanine hydroxylase gene, pretty similar. The PAH for short. The PAH gene is located on chromosome 12, and this disease, it's often caused by point mutations in the PAH gene, so just switching out one nucleotide for another, but it can also be caused by larger deletions or duplications. And this photo I have is just circling chromosome 12 where the mutation is located. In terms of clinical outcomes, babies are typically tested for this at around 5 days old. And without treatment, the buildup of phenylalanine can damage the brain and the nervous system, which can lead to learning disabilities. It can also lead to a host of other symptoms, including behavioral difficulties, very light skin, eczema, increased sickness, jerking movements and tremors, and also like a musty smell to the breath or skin or urine. And the primary treatment is to avoid phenylalanine, so that's going to be a low protein diet and the avoidance of aspartame. This disease can be treated with saproparetin, but the primary method of treating it is avoiding phenylalanine. These are my references. Thank you very much for listening.